Thank you so much. Thank you, Jim, Ben, Dharmendra, and all the organizers. It's great to be here. So I know I'm standing between you and lunch, so I'll try to first be on time and try to be entertaining as well. So the title of my talk is A Quest for Visual Intelligence. This is what most of us are excited about. And let's just look at the keyword intelligence or cognition for today's event. What does it mean to be visually intelligent? It's probably a good question. What does it mean for humans to be visually intelligent? Let me wake you up with a cognitive experiment right here, right now. So this is something I did when I was almost graduating from grad school. As a human subject, if you sign up for my experiment, I'll place you in front of a computer. You'll be instructed to stare at the center of the computer. And then what happens is that real-world pictures, photos, will pop up and quickly be masked by something like a wallpaper-looking graphics, just to erase that from the signal from your retina. Your job is to write down everything you've seen. And I try to pay you enough so you feel motivated to write it. So let's just give it a try. I'm not going to ask you to write it, but look at each photo and just tell yourself that what do you see, what the story is. I think most of you see interesting pictures. Probably you've never seen these pictures before, yet you have no problem telling what the content of the pictures are. More remarkably, these pictures are flashed really, really fast. Some of them are flashed about 40 milliseconds. That is 1/25th of a second. Yet your human visual system can comprehend these content of the picture and tell the story. In fact, this is what we found as well. So we showed this particular picture to a number of subjects, and we varied the presentation time. By 500 milliseconds, that's literally a split of a second, 1/2 of a second, humans can write novels, depending on how much you pay them. So in this case, the subject writes that this is some kind of game or fight. Two groups of two men counting the number of objects. One in the foreground was getting a fist in the face, outdoor because I see grass, maybe lines on the grass, making some mistakes here. That's why I think of a game, a rough game, emotion coming in, and more like rugby than football, and so on. So while we're celebrating the advance of AI and computer vision, I want to just say this. No computer today can do what humans can effortlessly do. We are very, very far from telling that story of what we see. This is really a figure that wakes me up every day and makes me excited to go to work. My dream with my students in our lab is to one day develop algorithms and enable computers to be able to tell that kind of story of the visual world that humans can. Not just to put a label, this is a cat or a chair, but really to understand what we see. And of course, I'm preaching to the choir here, if we generally can enable computers to see as well as humans or even beyond the human capability, we can help so many different aspects of our society. In fact, computer vision is already helping much of the society, but there's just so much more to come if we solve the problem of vision. So, where did all this begin? Computer vision as a field has a good birth story. And the good birth story comes in the summer of 1969. The field of AI was already born, had a few years of good development. The founding fathers of AI are thinking really hard about big problems. And a ambitious professor with a group of ambitious undergrads at MIT had decided in the summer of 1966 they'll solve vision. So that was the Summer Vision Project, is an attempt to use our summer workers effectively in the construction of a significant part of a visual system. So I know MIT has very smart students, but they didn't solve vision that summer. In fact, it's been 50 years. We're still on the quest for visual intelligence. Why is vision so hard? Why did we miscalculate how hard the problem is? Part of it is because it's just so effortless for ourselves. You open the eyes, you see the world, you understand what's going on, you do what you need to do. But the bottom line is measuring pixels is very, very different from understanding the scene. And this is the task that our brain has solved. So here is a very typical visual illusion to illustrate this concept. This is a famous monster illusion that everybody has seen before. You know they're the same monsters, they're the pixel copies of each other, but your brain can tell the story of a big monster chasing after a small monster. And the big monster has a very fierce look on his face, and the little monster looked scared. This is the difference between measuring pixels and understanding what we see. In fact, Plato has figured it out, as he figured out everything else. Many thousands of years ago, Plato already made an analogy of the task of vision is like these prisoners in the Allegory of the cave. The prisoners are tied on the chairs, forced to look ahead on a wall, and on the wall is the projection of a real-world play behind the prisoners, and the real world is in 3D and all this, and then a story is happening. And the prisoner's task is to be able to figure out the story behind them by seeing at the shadowed projection. And this is what you and I all did. Evolution has solved this. The visual world is projected from a 3D world onto our 2D retina. But we can infer what the real 3D world is. And computers one day need to achieve and do this in order to really understand vision. So the rest of the talk, I want to share with you very quickly a journey the field of computer vision has taken, especially my personal journey in this field. Before that, I do want to assure you we made a lot of progress. It is a hard problem, but even today, you're using daily products that are a result of great progress in computer vision, such as Google Street View, Microsoft PhotoSynth, the Kinect and Xbox, face recognition on your smartphones and digital cameras. So computer vision has done a lot of exciting things. But what about just telling what this is? Take a picture of this on your cell phone and ask, what object do I see? This seems to be a really simple problem humans can solve. Some of you probably recognize what this object is, especially if you're from Australia. What do you think Google think it is? It's a brown blob against the red background. So you might say, oh, this is weird. This is an animal I've never seen. It's a wombat, for your information. Well, this is easy. It's a coffee mug that all of us see, but Google thinks it's an orange blob against a light brown or yellow background. So even the problem of object recognition, something that's so innate to human vision, we have now solved it. So the rest of the talk, the journey is just going to be focusing on object recognition as a way to talk about computer vision. So let me just define object recognition for those of you who don't work in this field. One simple definition is give you a picture, object recognition algorithm would label this as a wombat. Not only this picture as a wombat, all of these as wombat, even though the wombat can be occluded, can be in different shape, can be camouflaged, can be cluttered. Or you have to take the camera 360 degrees or more and still be able to tell this is a wombat. So object recognition is not an easy task. So I'm going to put forth my claim of the day. I believe to solve the problem of object recognition or computer vision at large, we need to have 3 secret ingredients coming together to make this possible. And these secret ingredients are data, learning, and knowledge. And let me try to convince you with this. By the way, I think first of all, at the beginning, I thought of them in this kind of visual. So this is a little 3-leg stool. We have these 3 ingredients. It turned out everything under the sun is a 3-leg stool, from pest control to success. So what I really thought is, this is the 3-leg stool. These 3 ingredients have to come together and interact with each other in order to make this happen. So let's talk about the beginning. The beginning, computer vision was born in 1966, and immediately people jumped in working on the problem of object recognition. What was those days like? It's like the Jurassic age of computers. There was no data. There was little knowledge in statistical learning. Machine learning was barely around as a field, and internet didn't exist. Oh my God. And many of you were not born yet. So what did we do? Well, early computer vision scientists borrowed a lot of expert knowledge from psychologists. Psychologists have given us cognitive models of how objects can be composed by basic geometric shapes. Computer vision scientists like Tom Binford and his colleagues take this idea and implemented pioneering algorithms such as generalized cylinder and pictorial structure. These models capture the concept of objects are composed of parts, and the parts come together in a particular configuration, and that's how we recognize them. So the dawn of computer vision or object recognition was like this stool with 1 leg. In fact, it's probably a broken leg. But please remember these pioneers. They started the field of computer vision, particularly object recognition. So for the next 20 years, in 70s, 80s, and early 90s, object recognition was just too hard for most computer vision researchers to work on. So the field turned its attention to another problem and made great headways. And that's the 3D reconstruction problem. And that's outside of the scope of my talk. But a lot of good progress have been made in that. This is why we can use Google Street Views and so on. Now let's fast forward to 2000. 2000 is a special year. First, I entered grad school. Second, computer vision found the love of its life, and that's machine learning. And that changed the course of computer vision. It's like, microwave and ovens are invented for cooking. That really changed how we do things. If you look around, this was precisely around the time big progress have been made in machine learning. Important work such as SVM, boosting, graphical model, neural network were developed and start to be matured around that time. So computer vision made a lot of progress using those tools. This is a seminal paper in computer vision. Some of you should have read this. This was one of the first paper I read as a graduate student. In 2001, it's called Real-Time Face Detection. Viola Jones. In 5 years, 2006, Fujifilm rolled out the first digital camera that used this algorithm to recognize faces in the wild. In that 10 years, right after the turn of the century, computer vision as a field made tremendous progress in object recognition using all kinds of machine learning algorithms, from graphical models to neural network to boosting and so on. So we're starting to complete the leg of the stool. So while computer vision was really busy courting machine learning and falling in love, something else happened in this world, and it was really, really important. It changed all of our lives, and it changed the research of computer vision and computer science. Do you know what happened? Well, internet happened, and data has exploded. If you look at this graph, the data growth in the 10 years after the turn of the century to today is just exponential. And if you look at what's on internet today, just 60 seconds of it, most of these data are concentrated in forms like videos, pictures, speech, and text, multimedia data. In fact, Cisco estimated 86% of the data would be in forms of multimedia and pixels by 2016. Pixels are really the dark matters of the internet. So data is important, and computer vision field recognized that. Even in early 2000, when internet was just starting to grow, the field of computer vision is already putting together important data set that benchmark our progress in object recognition. European Union has supported this important work called Pascal VOC that has benchmarked our field for many years. That was around the time I became a faculty and started asking myself the question, really, 20 objects? Is that what the world is like? How many objects are there? I don't really know how many objects are there in the world, but I know it's more than 20. So I started to work with my student and think about this problem of big data before big data as a field existed. So we want to particularly ask this question, how do we go from 20 classes to millions for object recognition? And that is the ImageNet project that we put together starting 2007. ImageNet is a public data set that contains more than 14 million images, over 22,000 categories of objects and things, and it has helped the whole field of computer vision to develop object recognition algorithm that can tackle the problem in real world with big data. Compared to other data sets that we have worked with in this field, ImageNet was, I would consider, a big jump in terms of size. And because of ImageNet, many researchers around the world has been working on different aspects of the problem of object recognition, and we're really proud how it helped propelling our technology. One of the most important work is Jeff Hinton and his students' ImageNet classification with deep convolutional neural network, published in 2012, that changed the way we view deep learning technology. I want to remind you, the 2012 deep learning paper by Jeff Hinton mathematically is not that different from the 1998 paper proposed by Young LeCun called convolutional neural network. The backprog equations didn't change. But two things changed, and that changed our lives. One is hardware. Transistors following Moore's law, memories have just become more and more abundant. We have big clusters. We're able to do these build these high capacity algorithms. And data have changed. The amount of pixels or text or speech data that's available for training has empowered these algorithms. So these are two important things. So I have 2 minutes left, and I want to now ask myself and everybody the question, what's next? We talked about a little bit of knowledge, we talked about machine learning, we talked about data. In my opinion, next is knowledge. We need to come back and look at this. And here I'm at IBM. You guys are the first people recently to remind us the importance of knowledge through your work in Watson. There are many forms of knowledge, and they come to help visual recognition. For example, back to our wombat. A wombat is not just a wombat, it's also a marsupial, it's a mammal, it's an animal. If we use this ontological taxonomy knowledge, we can actually think about how we can reward our system with different information criteria and formulate an algorithm that can optimize between the information that our ontology provides as well as our recognition algorithms. And we have this work published recently, and instead of saying it's a red blob, it's a brown blob against red background, our algorithm EVA is capable of recognizing with 90% confidence it's a mammal. It's not quite there with wombat, but it did better with coffee mug. With 95% confidence, EVA can tell it's a coffee mug as opposed to orange blob. There are other forms of knowledge. A lot of us are working on this problem. What makes a chair chair? You cannot get 10,000 training examples for this chair and train a deep neural network and hope to recognize the next one that looks like this. These things don't come that often. What we really need is knowledge graphs and knowledge base that can help us and our algorithms to reason like humans by pulling in information from their physical properties to their visual properties to their semantic properties and reason about functionality. Also, social knowledge is important. People might look alike in their black jacket, but it's fundamentally different. One is a groom, one is a priest, one is a groomsman. So we use social knowledge to help us recognize events, social events like wedding, as well as social roles like bride, priest, and grooms. And finally, semantic knowledge. That brings us back to the original goal of this talk. How do we write a story of a picture? And without elaborating on the technical details, recently we've starting to close the loop and come back to the question that excites me the most, which is really truly understanding an image with this story. So this is one of the work, we call it the bi-directional mapping of images and text that uses a deep learning network and representation to map the contents of images as well as the contents of sentences. After we have learned this mapping, we can, we do very well in comparing with other algorithms as you can imagine, but we can do things like querying pictures out from a huge data set of images. I type the sentence, a young woman watches as a young blonde boy swings in a chair swing with buildings visible in the background. If you type this sentence right now in Google image search, you're not going to get much out of it. But by understanding sentences and images, we're able to do this. But I'm very, very excited to be working in the field of computer vision today. And I truly believe with the right combination of data, learning, and knowledge, we're going to make huge progress in the following few years. Just want to leave you to remind you, this is one of our ultimate goals. We want to be able to tell the stories, and towards that goal, we're taking data into the knowledge realm, and we're going from simple perception like putting a label of table or cat into reasoning. And thank you very much.